Okay,
Oh, pose the question. 0.15, 17, -5, all that point A. And then we got vector 4i plus 6k minus 9k. Pointing to some point B, as with the coordinates of BR. And it's obvious, we add the displacement in the x direction to the coordinate. Displacement in the y direction to the y coordinate, and so forth. And we find that the coordinates of B are 1 plus 4, 7 plus 6, -5 minus 5. 513 negative function. So what a straight line from here to here. We can describe that line. I say prove that R1 plus 2V lies in line segment between A and B and so forth. Okay, as long as T is between 0 and 1. Really hard to achieve proof until we define what a line is. Okay. So we actually define the line. And we're going to do that in a minute. But we can say that TV cross V has to be 0. Because that's just T times V cross V. And the angle between V and V is 0. So magnitude of V times magnitude of V sine theta is going to be 0. We should intuitively understand the cross product of parallel vectors. Is always because of that. They'll have the same theta. The same direction, so the theta is 0, so the sine theta is 0. Makes the cross product 0. Okay. We can put this into the context. Here's the origin, here's an R vector. R1 vector goes from the origin to this point, the coordinates obvious. We add that to the V vector, we get the R2 vector. Here it is. Okay. We could say that if T some number between 0 and 1, then we're adding a vector that's somewhat shorter than B. Okay. Makes sense. And if we take another T, maybe then we add this vector to the R1, we're going to get another vector. And then we can prove that this vector lies in the line. So basically, as you said, they kind of have the same slope, although we're in 3 dimensions and have the same direction cosines. So we could go with arguments like that, but you get the picture. As T increases, the length of TV increases along the same line. So that these vectors all define points along that same line. Okay. Now let's define a line, okay? Does that make sense? It's just R1 plus TV. Here's the TV. Here's R1 plus TV. Here would be for another TV. Okay, well. What can you say about the coordinates of the point on that line? Okay. For a picture, there it is, right? And well, put all that together. Our component is gonna be 1 plus 4t times I, right? Right off the rest of it. It's less than 2. So here's what we get. We just do the arithmetic and everybody gets it. So the equation of our line segment would be, another way of writing it is just the x coordinate is going to be 1 plus 4t, right? Because that's the terminal point of the R1 plus TD. And so just keeps tracing out points on this line. With x coordinate 1 plus 4t, y coordinate 7 plus 6t, z coordinate 5 plus 9t. And double check, if t equals 1, we get 5, 13, negative 14. There it is. Now the equation of the whole line. If t get bigger than 1, we get points on this side. Let's go all the way to infinity. We get the whole half line from here to here. If t is negative, we just reverse the directions. We get the whole half line going that way. So the line through AB without saying line segment or half line or anything is this, where t goes from 0 to infinity. Okay, well, now eliminate t. In other words, well, actually, solve each equation for t. Okay, now I did have a mistake here. Z is not 5 plus 9t, it's negative 5 plus 9t. Right there it is. Careless. Okay, so anyhow, t is then z plus 5. Negative z minus 5 over 9. Is that right? Okay. Everybody got that? So we can write this. Okay, this is totally equivalent to this because t, each of these things equals t, each of them equals each of the others. And totally equivalent to this on this, well, to this. Okay, depending on our restrictions on t. And what this calls metric equation of the line, this is parametric equation of the line. And really, it all comes down to that point, the vector in the direction of the line, to get the equation of the line. Okay. So point A, vector B. So A equals. Get myself in the writer. Okay, A equals X naught, Y naught, Z naught. The equation of the line is let's say V equals AI plus VJ plus CK, those kind of traditional letters that we'll use, okay? That's the way to write it. In general, moving from specific word to general statement. Okay. Or solving for T. I get T equals X minus X naught over A. That's going to equal Y minus Y naught over B. That equals Z minus Z naught over C. You want to not just memorize this or there for that. You want to understand the logic of this plus a multiple of this. Gives you this, gives you this, gives you this. If you want to go the other way, this gives you this, gives you this. Okay? They're all clear. Then you have a set of tools to understand the line and to do calculus line. Okay? Okay. So that's how we define our line. Now, we define a plane. We have a point X naught, Y naught, so you know what I'm going to call it A. And we have a vector again. And the plane's going to consist. Well, we're going to say the plane is perpendicular to B. Okay. Give you the general idea first. Okay, so whatever B is, there's a plane perpendicular to it. Or in any direction of space, and there's a plane perpendicular to that. The plane's defined by the fact that any point X, Y, Z well, we've got a vector from X naught, Y naught, Z naught to X, Y, Z. X, Y, Z is going to be in the plane, provided this vector is perpendicular to this one. Okay, well, this vector is clearly X minus X naught I, Y minus Y naught J, Z minus Z naught K. And I'll say on the plane perpendicular to V. If and only if this dot product equals 0. Okay. Well, multiply out the dot product, give me the equation of the line. Or the plane, sorry. Not sure where I stopped that last one, but I'm pretty sure I got all this. And I asked you to do this And you just do the dot product to get A times X minus X naught plus B times one minus one naught. Plus C times Z minus Z naught equals 0, and that's the equation of your plane. X, Y, Z is on the plane if and only if it satisfies that. Okay, so here's the equation of the plane. Okay. I promise you it's the equation of the plane. Give me a point on the plane and give me a vector perpendicular to the plane. Okay, so I had one person got the vector the first time I looked. I didn't look the second time, because the second time I was looking for a point. The vector is actually fairly easy, so I'm going to go with a point. Vector is easy if you know what to look for and you know how to look at it. I'm not sure everybody does. So I'm going to start with the point because everybody got that. After I gave the hint that you can pick any two of these, X, Y, and Z, and you get the other one and get a point, right? And then, you know, everybody picked at least one of those to be 0. I picked two of them to be 0. And then you get axis intersection. Okay, so actually we're going to get even more information about this graph. Okay, so they get let X and Y both equal 0. I said I was going to be nice to you. I picked just the product of those three numbers to be sure that every number was divided, right? I could have done 1,050, but I didn't want to make you think that much. Okay, I could have done a lot of things. I could have been multiplied this by 11. Okay, 1,050 plus 105 is 11. Not going to do that. Okay, so this point's on the graph. Well, you know what? You might as well. Locate that point. I got 35, that's pretty low, so we'll put that way down here. Okay, so here's 0, 0, negative 35. That was easy. Okay. Something there, I don't know what it is. Then we can easily get, okay, let Y and Z both be 0, you get X equals 21, right? So we have the point. Now I'm writing that pretty small. Let X and Y equals 0, you get 21, 21, 0, 0. And then let X and Z both be 0. You get Y equals 105 over 7. Okay. Which is 15. So right there's a triangle. You can kind of see how that triangle sloped. It gives you a pretty good representation of the orientation of the plane. And you kind of see where the rest of the plane would be, okay? So that's handy. So you got the equation of the plane, find the intercepts and graph them. Unless you know, one of the points is the origin, you're going to get a pretty good picture. Okay. Even if it is the origin, you got to think a little more, but not hard. Okay, so there's a plane. So we know that a normal vector would be like down and to the right. Forward, down to the right. Okay, or backward up to the left. Either way. We also know that this is the form has this form, it's gotta have this form. Okay. And now we know. Actually, we don't. I put these, all these coordinates into one thing. So. Epidemic of carelessness all on my own today. Not unusual. Thanks. Well, this tells me. That A is a coefficient of X, B is a coefficient of Y, and C is a coefficient of Z, right? Okay. So we have. What they go too far with this analogy. It could be this. So we have AX plus 7B minus 3C equals 21A. Of course, that's going to equal 105. Yeah. I thought this was a clever way to do it. But it's getting more complicated than it should be. So I can just make it a simpler statement. What I should have done in the first place. Apologies. The form has to be A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. Okay. That can be a range. Just multiply, distribute, and put your X's, Y's, and Z's here. And the AX naught and the BY naught and the CZ naught over on the side. This tells us that the number in front of X is A, the number in front of Y is B, the number in front of C is Z, right? I've gone to, went down a bad path there and making it more complicated than it is. But it's clear from this form that the coefficients of X, Y, and Z give us our A, B, and C for a vector perpendicular to the plane, right? So plane perpendicular to this vector, and right there it is. You can just read it off of the equation. Coefficient of X, coefficient of Y, coefficient of Z. Or mass and coefficients of I, J, and K. For your normal vector. Call them normal vector. Normal being perpendicular. Okay. So this plane is perpendicular to 5 odd from 7J minus 3K. A unit vector I haven't written what normal means, but normal means perpendicular to. Normal vector defines the plane, and the unit normal is very handy. It's easy to project on the unit normal. Is say that's 25 and 49 is 74, 9 is 83. Okay. And that's just the magnitude of the stuff. It's 83, little over 9. Okay. That makes sense. And again, I'm not really careful about the board. Just to reiterate. Weight of the plane is given as this. It has a point A, X, A, X minus X naught, B, Y minus Y naught, plus C, Z minus Z naught equals 0. Use a distributive law, you end up with AX plus BY plus CZ equals AX naught plus BY naught plus CZ naught. And that would work with any of the 3 points that you found. Plug in coordinates of any one of these points, and you're going to get 105 over here because of where you got the coordinates from. It follows that A, B, and C are just 5, 7, and -3, the same as the coefficients of X, Y, and Z. And of course, you can easily see that because the equation is this equation. Okay, this equation resulted from this particular vector, right? A, B, and C were components of the vector. So we can work backward very easily from the equation of the plane to find components of a vector perpendicular to the plane. And then a lot of times you want to find a unit normal, which we often get or label the letter small m. Okay. So all of a sudden we know quite a bit about lines and planes. Fairly simple, but not totally, because let's try something here. Now let's find. Okay, so well, here's the plane, right? We can now sketch a normal vector as actually wait myself enough for you to do what I want to do. Okay. Here we are. And a normal vector is going to have, and let's just put it right here. It's going to go 5 units in this direction, 7 units in this direction, and -3 units in the Z direction. It's going to go like this. In this little rectangular box that I drew. Tells you how it's oriented. Does that make sense? Yeah, it goes through these points, but it's not straight down. It's got to be tilted back here, so it hits the Z-axis here. And a vector perpendicular to it might look like this. Okay. I didn't draw this all to scale, didn't draw it all completely accurately. You'll see better pictures of the text in your homework. Now, how far is the point? Got a reasonable estimate where this point is. And here are the X, Y, And you can see what the Z coordinate at this point would be. You kind of see where it is. It's out here, this far, and then 3 units down. And let's say that point is 30, 50, -8. How far is that point from the plane? Well, you probably don't know. It turns out to be really pretty simple. All I have to do is go back to this point. And of course, this could be any point on the plane, right? Well, I don't want to go back to this point. If I know a point on the plane, I'll go back to it, okay? But I can pick any point on the plane. So I'm just going to pick this. I'm going to pick the one that closest to draw. Um, Here is my normal vector. Extending from the point 0, 0, -35, right? Now I want to draw a vector. From that point to this point. Okay, well, we'll put that picture down here without all the machinery. Here's my normal vector. There it is. This is the point. Zero, zero, -35. Here's my point. -30, 50, -8. And here's my vector from this point to this point, right? The distance from the plane is measured perpendicular to the plane. If the plane's here, and I want the distance from this point to the plane, I mean the closest point, and that's going to be at a perpendicular. Well, that distance is just going to be the component of this vector in the direction of the normal. Right here is my distance. Okay. So the component I'm doing an incomplete statement. I mean, the perpendicular component of the vector from the point on the plane to the point in the space is the distance we're at. I can draw a picture here. A little bigger picture. Label it. Oh, I've got my normal here. Normal vectors perpendicular to the plane. So we'll call this point on the plane A. Call the point in space B. We project at a right angle along this line. And this distance is the distance of the point of the plane. Okay. So if we went that parallel to this projection vector, we'd head up the point in the plane and would be perpendicular to the plane. So this vector trying to figure out what words we need. Perpendicular to the plane, and it is the distance at magnitude. I should say this my magnitude. Of this projection is the distance to the plane, okay? And that's easy to calculate. The magnitude of the projection is just equal to the magnitude of AB dot M. I want to go back to the projection, make sure you understand that. The magnitude of the projection is magnitude of AB times the magnitude of M times the cosine of theta. Magnitude of AB times the absolute value, cosine theta, cosine theta could be negative. You want to do this. Okay, that's a pretty neat idea. And it's really easy to compute. I mean, over here, I'll cover it up. I've really covered it up. I can't even find it, but we got the normal vector. 5i plus 7j minus. Okay, divided by square root of 83. That was AB. Make a positive, it turns out to be negative. And we got the distance. Fine. Okay. You're out there in interstellar space and space ogre comes at you. And you know your position and you know a plane that's a boundary to the safe area. You know what direction to go, right? How far you got to go. So, you know, you weigh that against the trouble of running from the ogre versus. Okay. You optimize your situation. Well, You're not gonna be in that situation. It's kind of like, you know, you're in a field. There's a fence. There's a bull charging you from the distance. Really fast bull. You're gonna run the closest point of that fence, most likely. Unless the bull haven't, you know, the closest point of the fence, yeah. So you gotta, it gets a little more complicated. How you can do it 3 dimensions, do it in dimensions. Because you can do projections and all this stuff in any number of dimensions. Okay. If you want to have 87 components to your vectors, you can do it. It's just more work. It's not any harder to set up. Okay. Yeah, that's kind of a synopsis of what you need to know about lines and planes. Now you got problems. Some of it might stretch you a little bit. Okay. But so far you seem to be on top of everything. Something you do pretty well. So take that for what it's worth. I'm just going to give you a quick idea about quadratic surfaces. We talked about it a little bit before. But basically, quadratic surface is just like a stack of ellipses or hyperbolas. The parameters. Okay. So remember what I told you. And I do recommend that you read that section, maybe try to look some of the examples. Yeah. Let's say you have the surface x squared plus 4y squared minus 9z squared equals 36. First of all, you can find the intercepts. Okay. But that's y equals 0, you get the z intercept, etc. What I want to do is this describes a surface. If its first powers of x, y, and z, you'd have a plane, which is kind of analogous to a straight line. Okay. If you have second powers, then you don't have a plane, you have curves. Okay. Okay, well. You want to be able to get a handle on these curves. I'm just going to give you an example. In the plane, z equals 1. What's our equation? In x and y. Well, according to John's, I'm not saying anything. But you know, what are you going to do? If the plane is z equals 1, you're going to set z equal to 1. And you're going to get x squared plus 4y squared minus 9 equals 27. Well, okay. Well, that's x squared over 6 squared plus y squared over 3 squared equals 1. And just divide by 36, right? Right. It's the square roots of those numbers. What's that mean? That means, well, if we're in the xy plane, as I showed you earlier, There's a lot more to the ellipse than this. There's focus and profile and all that stuff. But we know that the ellipse goes inside this box. Okay. Okay, what happens if we go to the plane where z equals 2? How does the ellipse we get in the z equals 2 plane correspond or compare to the ellipse we get in the z equals 1 plane? Well, if z equals 2, we get 36 now, right? Minus 36, we'd add 36 to this. We get this. Okay, which is like x squared over 7.9 squared plus y squared over 3.9 squared equals 1. About that right. And so we have here in that plane, we got bigger ellipse. We come out to 7.9. Here to negative 7.9. Here to 3.9. Here to negative 3.9. So this ellipse goes 1 unit above the XY plane. Like this. This ellipse goes another unit, it's bigger. So the ellipses keep getting bigger. Now, what happens in the XZ plane? Okay. And what happens in the YZ plane? In the XZ plane and the YZ plane, you got hyperbolas. And you got to put that together in the picture. Okay.